Hello, I'm Bob Sabin, a consulting engineer with Emerson's Industrial Energy Consulting team. Today, I'd like to address the control and coordination of utility and steam systems at industrial plants and mills, universities, and district heating operations. Many of these sites have relatively complex utility operations with multiple steam producers, a number of steam header pressures, and various steam users. Some also have steam turbine generators or gas-fired cogens in their configuration. And further, steam production may come not only from boilers and Hercigs, but some site processes might generate steam as a byproduct from normal running. What does all this complexity lead to? Well, unfortunately, it often leads to instability and reliability issues in steam system performance, as well as higher than desired cost. Mostly, this is because normal operation is nowhere near steady state. In a typical industrial environment, run rates are being adjusted, grades are changed, batches are being run, and equipment is coming on and being taken offline. All this brings considerable variation in normal day-to-day operation, and then on top of that, there are instrumentation and equipment failures occurring at times. The challenge that site operation has is to adjust steam system operating set points and coordinate all units in response to the variability that's being experienced. We can look at a drawing of a typical steam system and see how this is regularly done. Most often, sites manage steam header pressures with individual single PID loops. These control some combination of boiler masters, turbine inlets, turbine extractions, or pressure reducing valves like we see in the example here. This can be relatively effective at most times, though it's often accomplished by running with margin, buffers, or redundancy that can be quite expensive. But the single loop approach will struggle when there's higher than normal demand change or when there are unit trips. This is when it's not uncommon for significant interruptions in steam supply to occur. Situations where one upset or trip leads to another, or where cascading trips lead to the whole utility area going down. So what to do about this? How can the utility steam system be easily coordinated on a good day and also be able to automatically respond to the worst upsets at bad times? What's needed is a piece of control functionality that often doesn't even exist on a site. This is something that we call coordinated steam header control. As we see now, the yellow box is a control solution that manages the entire steam system as a unit, rather than having individual isolated loops trying to manage individual headers. Here we see that this solution can adjust all the devices and units that affect steam header pressure, and the beauty of it is that it can adjust each of them simultaneously. In upset situations, the coordinated control will use all available devices and units to make the moves necessary to stabilize the entire steam system and prevent one issue from causing other problems. This brings us to the question of how best to implement this coordinated functionality in our control system. In the past, it's been done with varying degrees of success by using layers of cascaded loops, overrides, and over-under controllers. But this resulted in very complex control configuration that was difficult to tune for all situations and was challenging to maintain over the long run. Our present approach is to leverage model predictive control for the coordinated header application. With the availability of MPC blocks within more modern controller instruction sets, this can be easily leveraged for this application. One beauty of MPC is its ability to deal with constraints. In a complex steam system, it's easy to arrive at a situation where a turbine section, PRV, or boiler is constrained and cannot be called upon to move faster or move more. These situations can be managed automatically with the MPC approach. The model knows at all times which combination of moves can best be made within limits to first recover from an upset and then to eventually rebalance in the most cost-effective operating scenario. So we've seen that managing steam systems can be difficult due to complexity, variability, and unplanned events. To effectively deal with this, it's ideal to implement an automatic coordinated header control solution. And to deploy this functionality in a way that's straightforward and maintainable, the use of MPC tools should be considered. The approach to implementing coordinated header control is consistent across all sites, but every steam system is unique with its own equipment complement, degrees of freedom, operating priorities, and constraints. Emerson consultants work with site operations and engineering personnel to document the process specifics involved and develop the operating scenarios and models needed for optimal operation. For further information, please contact your local Emerson office or visit us on the web. Thank you very much.